Today we want to look at an example of writing a double integral for the volume of a solid. We're going to be thinking of this as the volume of the solid under a surface and above a region in the XY plane. So here, with this orientation, I'd say I want the front half of this of the solid under the paraboloid and above this semicircle. So above the circle x squared plus y squared equals 4, where x is positive. So in the first and fourth quadrants, like we have here. So what we'll want to do is take a look at the region that we're plugging in to our function, because we've set this up in our favorite way. We've set it up as the space underneath a function and above the set of inputs for that function. So let's look at this from the top view. And I've got a semicircle down here that I have to describe for the double integral. So down here is a semicircle. That's the generic region R in our double integral. So the volume of the solid is going to be a double integral over this region R, which is a semicircle of the function dA. So we're going to write this double integral. The function we have, 4 minus x squared plus y squared. We know that's a circular paraboloid. That's going to be one of our favorites. So our primary job is going to be describing the region. This region R is this semicircle. Let's take a different look at this semicircle. I've got the XY plane. I'm only concerned with what's going on in the first and the fourth quadrants. And so here is our region R. I'll try outlining it and highlighting it in the same pattern that I used over on the 3/4 view. So this is the floor, and the walls and the ceiling are formed by the paraboloid 4 minus x squared minus y squared. Now, this is a part of the circle x squared plus y squared equals 4. That's where this paraboloid is going to be intersecting the xy plane. Notice that this circle is the paraboloid where the area or the line, words are hard today. This circle, x squared plus y squared plus 4, is where the paraboloid hits the xy plane. So if we look at f of xy equals 0, for a height of 0 above the xy plane, that's going to give us 4 minus x squared plus y squared equals 0, or x squared plus y squared equals 4. So we want all of it. And then later on, we can restrict to some piece of this and just describe it differently. But right now, we're taking all of it. And here's the line. This is the circle. X squared plus y squared is equal to 4. So this tells us some stuff about what's going on. First of all, our x's, if we just go with the intervals that contain our x's and y's, our smallest x value is 0, and our largest x value is 2. Our smallest y value is -2. And our largest y value is 2. So depending on which double integral we're setting up, if the outer integral or the last integral is y, then it's going to go from -2 to 2. If the last integral is x, it's going to go from 0 to 2. You can go this way or go this way. So now we just have to set up double integrals. So notice what we have here. I can't write y as a function of x. That's a little bit tricky. I can write y as 2 functions of x. So there are a couple of things that we can do. I can take my x squared plus y squared equals 4, and I can say this is y equals plus or minus the square roots of 4 minus x squared. This is going to be the top semicircle and the bottom semicircle. We can also solve for x in the same way. So this is the top and the bottom. We can solve for x in the same way. So x is this plus or minus the square root of 4 minus y squared. These are the right and left semicircles. So this is right and left. In our illustration, we can see that I need the top and bottom. So if I start making y variable, I'm going to need the top semicircle and the bottom semicircle. But in terms of x, if we're going from side to side, I only need plus the square root of 4 minus y squared. So up here, the top and bottom, there's plus square root of 4 minus x squared. And then the bottom semicircle is minus the square root of 4 minus x squared. But in terms of this problem, this whole semicircle is where x is positive square root of 4 minus y squared. That's the right semicircle versus the top and bottom semicircles. Now, the reason I only wrote quarter circles for the plus and minus 4 minus x squared, that's because I'm not concerned with this, what's going on in quadrant 3 and quadrant 4. Not worried about those parts. So let's use this information to write our 2 double integrals. Remember, we can always do this in 2 different ways, a dx dy and a dy dx. The one that we use will be the one that's most convenient to us. Sometimes it doesn't matter. So we're going to be describing our region. We've got 2 choices. My function looks like 4 minus x squared minus y squared. That's going to be the case for both of our double integrals. And I realize I switched x and y from orange and green to orange and blue. So I hope that doesn't mess anybody up. Now it looks more Mets than it does Halloween. So yeah, I don't like it. So remember, when we're setting up a double integral, we always go after the last integral first. We always set up the last integral first because the last integral only gets to use constants, and the constants are easy to pick out. So for dy, if that's the last integral, we're going to integrate from -2 to 2. So we'll go from -2 to 2. Then we'll pick a typical y value and see what x is between for all the y values. So our thinking is, for all the y values between -2 and 2, we care about the x values that start at 0 and end at that semicircle. So x will start at 0 and end at positive square root of 4 minus y squared. Now I've got my dx dy integral. We would first integrate 4 minus x squared minus y squared with respect to x, and then we'll plug in 0 to the positive square root of 4 minus y squared. Always write down your last interval first. Pick a typical one of those values and say, what's the other variable in between? When the y's go from -2 to 2, pick a typical y and think, what's x between? And then just turn that whole process 90 degrees. If we set up a dy dx integral where dx is going last, the x interval is the easy one to write. X goes from 0 to 2. Now we got to figure out what y is between. So we pick a typical x value and see what's y between. Y is at the lowest, the bottom semicircle, and at the highest, the top semicircle. So we'll integrate y from the bottom semicircle to the top semicircle. So it looks a little bit different depending on what half we're going after. In each case, there's one that's being cut in half. In the first, in the dx dy integral, the y goes from -2 to 2, that full range. Then the x's are the ones that are cut in half. X goes from 0 to plus and minus to the positive square root. In the dy dx integral, x's are still cut in half from 0 to 2. I don't get that full circle because I don't have any circle back here. But the y's go from the top to the, or from the bottom all the way to the top. Full paths in the y. How's everybody okay? Is it too simple? Or is it too early? This is why I don't play poker with students. Because no matter what happens, y'all are just looking at me. You're like, oh, I go all in, and you look at me like, I could even deliberately be trying to piss you off. I'd be like, check raise, and you're like, man, I'm not gonna play poker with y'all. You are too cool for that. The only real dangerous thing that I have that could provoke a reaction is like a word that you can only use sparingly when you're a teacher. Ah, so we're like betting, and you make a bet or something like that. I'm trying to figure out if you're lying or not. So I'm like, oh, hey, what do you think of that test coming up? Oh, there I do. Try to throw you off the game. All right, let's calculate these. Now, we don't have a formula for the area underneath a circular paraboloid, but I wanted something that we can integrate. Sometimes we do this problem with like finding a part of a sphere, but these are really inconvenient coordinates for round stuff. Rectangular coordinates are really inconvenient for round things, like no shit, right? The coordinates are set up on a rectangular grid. It's really hard to smash circles onto that. That's why we're eventually going to have different sets of coordinates that are better at round things. But let's just integrate this one. I picked this specifically so we could integrate it. That was the point. I keep looking at this example, Michael. Why did you pick one that you intended to integrate? Because now you have to integrate it. Son of a. All right, that's fine. That's fine. I'm going to do this first one first. We integrate from -2 to 2 on the y, and from 0 to the square root of 4 minus y squared on the x. In the usual fashion, we don't write the x equals and the y equals on our double integral because the dx dy is telling us which one is which. Also, this first integral has a function of y in it. It must be the x integral because I can't have y equals square root of 4 minus y squared. So that tells us that we're integrating with respect to x. So I'm going to have a 4x minus 1/3 x cubed minus xy squared. And then this gets evaluated from 0 to the square root of 4 minus y squared. Once again, it must be plugging in for x because I got a function of y right there. So now we still didn't integrate from -2 to 2. We're going to have to do that afterwards. So now we got to plug in the square root of 4 minus y squared into where we have all these x's. Still haven't integrated with respect to y, so I have to keep writing that, but I got a 4 times the square root of 4 minus y squared minus a 1/3 times the square root of 4 minus y squared cubed minus y squared times the square root of 4 minus y squared. This will be plugging in the top minus, these all have an x, so 0. This is still an integral with respect to y. Parentheses, parentheses. F of b minus f of a. Good. Any questions? Algebraically, it's messy, but we're just doing our normal thing, plugging in the endpoint and subtracting. Now I've got kind of a messy thing going on here, but notice that there's a common factor of 4 minus square root of 4 minus y squared. So now we're going to have to do some algebra stuff. I'm going to pull the square root of 4 minus y squared as a common factor. And that's going to leave behind, let's see, just a 4 from this term, minus 1/3 of a square root of 4 minus y squared squared, because I had 3 of them, I pulled one of them out, so I got the square root of 4 minus y squared squared minus, took this out, y squared. Are we okay with that? Factoring out our common factor. I'm never okay. Nothing on my sleeves. Sometimes algebra is like, oh, wait. No. Now I've got the square root of 4 minus y squared being squared, so that we can simplify. So that is just going to be 4 minus y squared. And that's getting multiplied by a 1/3. So inside I've got a 4 minus 4/3 plus 1/3 y squared minus y squared. So I'm just going to distribute the negative 1/3 to the 4 and the negative y squared. And then because I planned so perfectly badly, we're gonna have to flip pages because I did not give myself enough space. If you had a professional teacher, this kind of shit wouldn't happen, but you're stuck with me, so deal with it. So, but we've got 4 minus 4/3. So I got, what, 12 minus 4 is 8/3, minus 2/3 y. Scroll up. So I'm still integrating from -2 to 2, and all of a sudden I don't like this integral anymore. I've got the square root of 4 minus y squared. And left over on the inside, I've got 4 minus 4/3 is 12/3 minus 4/3 or 8/3. And a third y squared minus y squared is going to be 1 minus third minus 1 3/3 is minus 2/3. And this is still an integral dy. The other thing that we might want to notice here is that I've got 8/3 minus 2/3, and we can see the square root of 4 minus y squared. That means this shit's about to get very messy. And I'm really questioning whether I want to finish this problem or not, or to say the rest is left as an exercise to the reader. That's like the ultimate math book cop-out. Like anytime you're reading a math book, it's like, oh, this is left as an exercise to the reader. That's the author saying, ugh, and then like just bailing on the problem. The other way we'll do that is we're like, oh, it's clearly obvious that. It's like, oh, dude, you're writing the book. Say the obvious thing. It's a textbook. It's supposed to be instructive. Just say the obvious thing. That's further evidence that textbooks are written for other teachers, not for students. But notice I've got these thirds running around. In particular, there's a 2/3 running around. If we want to clean that up because we know we're going to be integrating something messier, we can pull a 2/3 out of this whole thing, because the 8/3 and the 2/3 have a common factor of 2/3. And that's going to take 8/3. We'll factor out 2/3. That's going to leave a 4. And a 2/3 y squared, I factored out the 2/3 is going to be a 4 minus y squared. Now, is this the only way we could have ended up at the integral from -2 to 2 of the 4 minus y squared to the 3/2? No, probably not. This just happens to be the way that I ended up getting there. How's everybody okay? To continue this problem by hand, we would have to do our favorite technique in all of integration, which would be trigonometric substitution. That's the one that we have at this point. We're not doing anything fancy. So we'll do a trigonometric substitution. The case that we're going to be using is sine. So our answer is presumably going to have some arc sine somewhere. That's where the pi is going to show up. We should be not surprised that arc sine, that trig substitution showed up, and that we're going to have some arc sines running around, because the region over which we're integrating is a circle. It's a part of a circle. And circles need pi for their volumes and their areas. The other thing that we could do is we could at least just, at the very least, now that we've got it down to integral of a single variable, we could grab our calculating machine and plug that in. This calculator will not handle double integrals. So single integral, once we got it down to a single integral, then we can deal with it that way. So two things. We would use trigonometric substitution to continue from this point. The trigonometric substitution that we would want to use is that y is equal to 2 times the sine of theta. And that will make dy to cosine theta d theta. At this point, our integral looks really clean, so we might be confident. The other thing that we can do, we can pause here. We can pause here, use a machine to check the value against another double integral. So what I mean is, I've got 2/3 times, where is it, math? F an integral of 4 minus y x squared. I'm going to use x. Oh, I've got fancy printing on my calculator. I got 4 minus x squared to the 3/2 dx. So it looks like we're coming up with 4 pi. Now it's ridiculous to actually, to complete the problem, this is only like halfway. If I wanted to do this double integral and I was going to pull out a machine at some point, I should just drop a machine on the very first part of the problem. I should just find a machine that does a double integral, put the double integral in, have it calculate that for me, if that's the route that we wanted to go. But we're doing a specific thing. I want to check this against the other double integral before I proceed with trigonometric substitution. Any questions? How's everybody okay? Kind of a non-committal answer, because you're like, oh, dude, you just said trig substitution and then asked if we're okay. So right now, our only concern is, are you going to make us sit in this room and do trigonometric substitution? And the answer to that is no. I'll make you sit in some other room, give you plenty of time to work out trigonometric substitution if you have to do that. I would never ask you to do a trigonometric substitution in Calc 3. You've already had tests on fucking trig subs. But for like homework and like practice, everything is off limits. Everything is permitted. So I've got 2/3 the integral of 4 minus 2 sine theta squared to the 3/2. When you're doing substitution, all the y have to become theta. So I also have a 2 cosine theta d theta. I like to have the reminders of trig sub how it works. Remember mainly because we all come from different backgrounds. I don't know how you get along with trigonometric substitution. The whole reason behind picking sine case for this is we had a 4 minus y squared. That's going to take 4 minus sine squared. That's going to use the 1 minus sine squared is cosine squared. So this trigonometric substitution is to take these two terms and pull them into one term. Trigonometric substitution is integration Thunderdome. Two terms enter, one term leaves. So this 4 minus 2 sine theta becomes 4 minus 4 sine squared theta, which is 4 cosine squared theta. And then that's getting raised to the 3/2 power. When we raise things to the 3/2 power, the easiest thing to do is the half power first, because that makes things smaller. So 4 to the 3/2. The square root of 4 is 2. 2 cubed is 8. So it's going to be 8. Cosine squared. The square root of cosine squared is cosine. Raised to the 3rd power is cosine cubed. So all this becomes 8 cosine cubed. And so the point of our trigonometric substitution was to get us to 8 cosine cubed for this 4 minus y squared to the 3/2. Now we still have this times 2 cosine theta d theta. Notice that I'm not integrating from -2 to 2 anymore. I'm not integrating from -2 to 2 anymore because those are y values and we have theta. Also notice I've got an 8 and then I got this 2, so I could pull those out. So that's 16 times 2, we got 32. I can pull these constants. And I've got a predictable even power of cosine, which is one of the things that can happen when we're doing trigonometric substitution. Remember, when you're doing trigonometric substitution, your theta integral will be one of two forms: even powers of cosine or odd powers of secants with no tangents. Those are the two things that can happen: even powers of cosine and odd powers of secants without tangents. Because those are the two products of powers of trig functions that aren't substitution integrals. If we have an odd power of cosine, it's a substitution integral. If we have any kind of secants with tangents available, that's a substitution integral. Trigonometric substitution is for non-substitution integral. If there's a substitution in your theta integral, there was a substitution in your y integral, go back and get that substitution. The other thing that we want to point out is that we're not integrating from 2 to 2 because those are y values. We want to point out that we're not integrating from y equals -2 to y equals +2 because this is a theta integral now. We're not integrating from -2 to 2 because those are y values, and this is a theta integral now. Raises another important question. Can we trade our y's for thetas? Yes or no? Why or why not? So here's what's left for you to do on this problem. Finish your integration. First of all, decide if you can trade your y equals 2 to for y going from -2 to 2 for thetas using y equals 2 sine theta. Will that be okay? Will that make sense in the context of this problem? Or will things you call cancel out? That's number one. Number two, either do that and continue the problem, or find the antiderivative, take it back to y, and then finish your integral and verify that it comes out to 4 pi as the machine predicted. Then we're still not done because we got to go back and we had this whole other integral. Now you can see we're going to be plugging in some square root of 4 minus x squared, and that's going to lead to some more trigonometric substitution. So use both those integrals to get some insight to this orange question. All right. That's going to do it for today. Think about that orange question. Proceed with this integral. Go back and do the other double integral to make sure that we come up with 4 pi. All right, that's it for today. I'll see you all on tomorrow. Everybody have a good day, and thanks for playing.